Thank you, Dr. Shubhajit Pashu, for inviting me here for this lecture. And this is a very difficult topic to talk about because there are subtopics inside this domain. Each of those subtopic actually takes 1 hour or so. So that's the difficulty. So I was told that I should keep it as basic level as possible. So I have tried to do my best. So let's see. So feel free to stop me at any point during the lecture, and I will try to answer if you have any questions. Fine. So that is an overview of quantum information and computation. So I guess all of us know what is classical information and computation. So before I go over to quantum information and computation, I will, in the introduction, talk a little bit about classical information and computation. Then the outline is as follows. Little bit of quantum mechanics as the background. We'll discuss some experiment. Then we'll study some postulate, followed by quantum information, its representation, no-chronic entanglement. Finally, I will conclude with some bits and pieces of quantum computing. So classical information, all of us know, it deals with some system. So it could be any computational system. It can be desktop or a laptop or a CPU or an embedded system or a microprocessor or a microcontroller. There are many kinds of systems. Then we talk about state. So every system has some internal state. For example, if we talk about the traditional CPU, so the contents of all the internal registers of the CPU and the internal memory, so that content together can be thought of as the internal state. So even if one bit of any one of the register or any one of the memory locations changes, we can think that okay, we have a state change. Then information, classically information is represented in terms of bits, binary values, and physically they are represented either by high voltage versus low voltage, or high current versus low current, or maybe a capacitor is charged versus discharged. Okay. So there are many ways to represent it. Okay. The classical computation, so the link between information and computation is nothing but information processing. So when you have some information, you want to take it as an input, then you want to process it, do something with it, and then squeeze out some output. So that is precisely information processing. Then to do that, we need to manipulate classical logic signals, 0, 1 or their representation, to form small functional unit, so that we can do 1-bit operation, 2-bit operation. That gives rise to different gates that we study in digital logic, computer organization, computer hardware. Then we combine gates to build circuits and combine circuits to build signals. Then mathematically we study this entire domain in an abstract model called Turing model of computation, where again the state that I am talking about, the internal states are modeled as some points or some members of a set of states, and then the evolution of the register values or the memory values inside the computer is modeled as state transition. And when the computer produces an output and the program stops, that is modeled as the Turing machine reaching its final state with a specified output. Okay? So that is pretty much standard in classical computation. Now when we go to quantum computation, some notions of classical computation will apply, but some new notions will emerge, as we will see. So we need to build some background in order to prepare our mind for quantum information and computation. So I will refer to a very old experiment in physics. So there is a source of light, okay, and we have two very small slates. So this is, so light cannot pass through except these two slates. Now we have a detector screen, so where maybe there will be some fluorescent material, and that can tell you that at what points exactly the light path follows. So what happens is that when you have a high intensity light, then if you stop say slit 2, you see this intensity pattern, which is kind of expected. Okay. So this is intensity at different point. So the high intensity is represented by high amplitude, low intensity is represented by low amplitude. Okay. When you close slit 1 and use only slit 2, then you observe this kind of intensity pattern. And when both are open, then you observe this kind of intensity pattern. Why? Because there is interference between the waves, and we know that these amplitudes are nothing but vectors. So sometimes the vectors are added in order to amplify, sometimes the vector subtracted, they are in opposite direction. So we have this pattern of high and low. Okay. Now, what happens when you reduce the intensity? So when you reduce the intensity, then smaller and smaller amount of light goes through. And at one point of time, it is observed that such kind of continuous spectrum is not possible. It is observed that only, for example, corresponding to slit 1, we have some local area where the light is concentrated, and corresponding to slit 2, there is another area where light is concentrated. So it will come like this and this. Okay. So that is, that tells you what? That tells you that instead of light, if we had some particles, say some small bullets, then also you would have observed that kind of thing, because some bullets will pass through the top slit, and some bullets will pass through the bottom slit, and will have exactly two distinct locations where the patterns will be confined to. So that tells you about the particle nature of light. So this tells you about the wave nature of light. But when you reduce the intensity, so if we think of light to be consisting of many particles that are called photons, so if the intensity is reduced, that means at a time you are sending less number of photons in one shot, and eventually probably you will emit even a single photon. Now what happens that if you reduce the intensity even further down and slow the process, so you imagine that I have a source which you can control, which you can very precisely turn on and off. Maybe you have a laser pointer, today's language, okay, or a single photon source. Then what happens is that, so if you slow down the process, so one photon comes, and then after a long time another photon comes, then what do you expect? You expect that, okay, because I have reduced the intensity and slowed down the process further, then of course these two regions will be concentrated with light, because I am expected to observe the particle nature of it. Okay. But surprisingly, that particle nature is observed when one slit is closed. So when slit 2 is closed, we observe that, okay, there is a spot here. When slit 1 is closed, we observe that there is a spot here for very low intensity and very slow emission of light. But when both the slits are open, then we observe a wave-like pattern like this. So then the scientists were bewildered that what could be the explanation, because my rate of emission is very, very slow, so I am allowing at a time potentially only one photon to emerge from my source and giving it sufficient time, okay, to reach and do some interaction. And the next photon is coming after a long time. So the single photon should, because it is a particle, right, it should go either through slit 1 or through slit 2 at a time. So it should hit exactly at one point, and over a period of time you should see two localized portions. But a single photon itself is, itself displays such kind of interference pattern. So the only explanation is that probably the photon passed through both the slits at the same time, and that is really counterintuitive, because how can a particle pass through both the two slits which are separated in space whose dimension is more than the dimension of the photon? So that's the kind of strange behavior that we observe in the quantum world. Okay. So we all know about wave-particle duality, and this experiment initially it demonstrated that okay, light has both wave nature and particle nature. That can be understood. Okay, if we give high intensity light, high frequency light, then we have wave nature, because a lot of photons are there together, so we cannot distinguish the particle nature. If we have a single photon or small number of light particles, then we have the particle nature. That is fine. But interestingly, if we go down further the scale, then even the particle shows wave nature. And at the same time, so at the same condition of the apparatus, at the same frequency of emission, at the same reduced intensity level, just shutting down one of the slit shows the particle nature, because it will hit here or here exactly. But keeping both the open shows the wave nature. So that is really counterintuitive, because at the identical condition, no change with the source, because it's coming from the source. I am not changing anything. I am just changing how it will go. So that means then people try to tell that okay, so is the particle aware of what I am doing? Whether I am, so that means when I am shutting down one of the slits, so is the particle choosing to show the particle nature, and when I am keeping both the slits open, is the photon choosing to show wave nature? So has photon some kind of intention of its own? We don't know yet. So still there are many theories, many models to explain why physically such kind of things happen. But even on today, it is nobody can tell you why it happens like this. We only know what happens when, and we only know how to use them. Okay? We do not know why it happens. So that is one peculiar thing which is different from classical mechanics in the quantum domain. So when you go to subatomic particles, the usual laws of physics do no longer hold. You cannot apply Newtonian mechanics here, even if you consider light as a particle. Okay, so another interesting experiment that dates back to 1922 is Stern-Gager experiment. Again, the arrangement is quite simple. So we have a magnetic field applied vertically along the path. We have a source of silver atoms, and this vertical magnetic field is non-uniform. That means the gradient is different at different points in space. Okay. So what do we expect? We expect silver atoms are going through this magnetic field which is non-uniform in nature in the vertical direction. So it will apply non-uniform deflection to different particles, and we are expected to have a continuous spectra on the spring. But again, this experiment shows that the spectra is confined to two specific levels. So some of the silver atoms are deposited here and some are deposited here, and we say that the silver atoms that deposited here that have a spin plus half and the other one have a spin minus half. So this spin is not a physical spin like like something rotating on its axis, but this is just a vector quantity, and the name is given because of its relation to this magnetic direction. So this also shows that, say, the magnetic the magnetic spin of a particle is quantized. So that means even if we force it continuous deflection, still the particle chooses one of very few quantized states. Here it is two possibilities, it could be 3 or 4 under different contexts, but it is so. Okay. So now let's try to go to block diagram of these details. So we try to summarize, similar experiments and try to extract some idea how things work from it. So look at this. Here we can actually label the coordinate axis. So in the room, if we say that okay, x direction is this direction from say N to S. Okay, y direction is the direction in which the silver atoms travel from the source to the destination, and z direction is the perpendicular direction, perpendicular to both the x direction and the y direction. Okay. So in that case, this kind of deflection will measure whether it is going in the plus z direction or in the minus z direction. Okay, and that property we call that we are measuring the spin in the z direction. Okay. So it will be either up or down. So similarly, if we can rotate the arrangement so that the magnetic field is applied not in the z direction but in the y direction, so I can actually, so here the magnets are in the top and bottom, I can rotate them like this. Okay. The path will remain the same, but I am just changing the arrangement. So in that case, we'll measure the spin in the plus x or in the minus x direction, and similarly plus y in the minus y direction. It is possible. Okay. And because the magnetic spin is a three-dimensional vector, so we will have x, y, z components. So any one of the components can be measured. Okay. So that is the thing. Now the question is, suppose I send 100 silver atoms, okay, and measure the spin in the z direction. Okay. So because things can be assumed to be uniformly random, so it is expected that say 50 of the atoms will show up z up spin and the rest 50 will show z down spin. Okay, that's what is expected. So now, and that's what actually happens when you do the experiment. So there is perfect correlation between what is expected in theory and what you observe in practice. But now, suppose I block these 50 atoms that show z down. I only allow the 50 atoms that show z up. That means I collect only these particles and allow them to go through. I don't allow the bottom ones. Now I measure the spin of these particles in the x direction. Okay. So what is expected? The expected is, because I have measured only up property. So here we should get up. All the 50 should have this up value. But surprisingly, even measuring in the x direction randomizes the thing, even if it chooses to collect only the up particles. So if we initially had 100 particles, 50 here, 50 here, so we allow them, so roughly we will observe 25 are showing up direction and 25 are showing down direction. What is more interesting is that then one could conjecture that okay, so probably z and x are uncorrelated. So probably we have z up and down that is independent of x up and down. So that could be one possible explanation. But then the next one is even more surprising. So I have z measured out of 150 up, 50 down. Then I have out of those 50 z up, I have x measured. So out of them 25 x up, 25 x down. Right? Then I block these 25 x down also. I allow only those which were initially z up and now x up. Okay? And up to this point, the only possible explanation is that z and x are independent. But when I again measure in the z direction, because z and x are independent, the expected thing is that whatever was x, I don't care, because the z value was initially up, I should get up in the z direction. Right? Because these are precisely those particle x should not influence z. Just like z did not influence x, because when we measured z and collected only the up ones in the z, it did not affect x. Because it showed both x up and down. So z did not affect x, so x should not affect z. So I should get only z up because I started with z up. But surprisingly, it shows both z up and down. Again, roughly 50% would go to the up direction and 50% would go to the down direction. So again, this is very counterintuitive. And it is very difficult to explain in terms of our classical notions of physics, that how these things happen. So I discussed 2 experiments, and there are many more which actually show this peculiarity of the quantum world. So next the question comes that how we can study such quantum system, such behavior. So like in any scientific domain, be it classical physics or chemistry or biology. So what scientists do, they observe something in nature, then they try to explain and they formulate the law and create model out of it. So when you create the initial model by some natural observation, you cannot prove anything. Because whatever you are observing, you just try to justify it, you try to frame some laws and try to match your model with whatever you are observing. Now 2 scientists can come up with 2 different models, and out of them the model which will predict the world better, which will fit the observed data better, that model will be chosen. Okay. That's what people do in machine learning following Occam's razor. The same principle is followed by scientists since thousands and thousands of years in choosing any model that tries to explain the phenomenal world, the nature around us. So, when scientists tried to formulate the laws of quantum mechanics, so they tried to come up with a mathematical model that will capture these strange behaviors, some of which we explain through some experiments. So the underlying mathematics will also have some strange behavior which cannot be explained. So that gives rise to an axiomatic theory. So in an axiomatic theory, you cannot question the axioms. Okay, so you have to accept it on blind faith. And from the axioms, now you can apply your logic to derive new results. Okay. And if person 1 comes up with say 5 set of axioms, person B may come up with different say sets of 7 other axioms. Okay. So again, which one will survive? The one which will again explain the world better, okay, which will fit the data better. So all these kind of strange experiments, in order to formalize them, physicists have come up with few postulates. So I will enlist only the important ones of them, not all, and in a simplified, as much simplified form as possible. And you may ask that why such strange rules are there. As I proceed, it will turn out to be even stranger. Because that's the only way to explain what happens in the quantum world. So if you use some other kind of mathematical model, it is found that it does not explain it well. And there is no question to ask that why this model works. So postulates are like axiom. So first postulate is about state. So we discussed in classical computation, state is nothing but the configuration of the registers and the memories, say in a system, in a computer system. Okay, and we have state transition in all. Now in the quantum world, state is an analogous quantity. Okay, so we can talk about state of the position, state of the velocity, state of the magnetization, state of charge containment. So it could be any state. where some change of state possibly occurs by interaction with the environment. So the axiom is such that associated to any physical system, there is a complex vector space. So I will try to explain with inner product known as the state space of the system. So again, state space is nothing but a set of states. So just like in your computer system, you have a set of states which you represent in terms of state diagram, right? So in here also you have a set of states. So for example, in our earlier experiment, we can talk about when we measure the z direction, we have only two states, right? One is up state, one is down state. So our state space, the size is 2. That's the most simplest form. But in general, it could have many different values. Okay. So that's the state space. And any state, say for example the up state or the down state, okay? Or if you talk about say photon polarization, whether it's say vertically polarized or it's horizontally polarized. So that is the state of a photon. So any state is mathematically represented by a vector. And what kind of vector? Vectors we know nothing but an ordered tuple of scalars. That's the vector. So here the scalar happens to be complex number. Okay. So we have every state can be represented as a complex vector. That means a vector whose every coordinate value can be represented by some complex number. Fine. And the system is completely described by state vector, which is a unit vector in the system state space. Okay. So why inner product? So when you talk about vector space in general, so we may have a vector space, an n-dimensional vector space where we can represent vectors as points, or we can represent vectors as arrows from the origin, or we can represent vectors as an ordered tuple of scalars precisely the coordinates in some particular basis in that space. So we project it on some basis and then we measure the length. So all representations are equivalent. So it is also a point, it is also an arrow, and it is also a set of points. The same object represented differently. So here the coordinates happen to be complex. Now you can ask that, okay, if I have a complex number, say alpha plus I beta, right? So suppose z1 is my complex number and z2 is my another complex number, say gamma plus say I delta, where I is the imaginary unity and alpha, beta, gamma, delta are real numbers. Then I can write one vector as z1, z2. Okay? So this is one vector in the two-dimensional complex vector space. Now, so this is just a model. So we know that any complex number is nothing but a pair of real numbers. So a vector, a two-dimensional complex vector space could very well be represented by a vector in a four-dimensional real space. So I could just write alpha, beta, gamma and delta like this. So it could be a real vector. So then you can ask them, okay, why we are not using this? And there could be other forms of representation also. So as I am saying, it's the same thing. So physically it is the same quantity. I can model it many different. But historically it has been, it has been such that this kind of model are explaining the things better. They're easy to do some other calculation, transformation, other operations. That becomes easy to interpret. So manipulation of states, change of state, that becomes easy to induce. So that is the only reason. Otherwise, one could come up with an equivalent representation which could be much simpler. Okay? So to that end, things are still okay. Anyway, so if we have a single particle, say a photon or an electron, which has just two possible states, then it will be a vector in two-dimensional complex vector space. If we have n particles, then it will have a, it will be a vector in 2 to the power n dimension. We'll see it later. Evolution of a closed quantum system is described by unitary transformation. So again I will explain what it is. So you have a quantum object, say a photon or an electron or a particle, right? So suppose this is a quantum particle and I am trying to apply some kind of operation. So let's say this is the particle as input and doing some kind of operation or state change basically, and the same quantum particle is coming out. Okay? And we have already seen some experiments related to that. For example, measuring the spin in the z direction, we have a big apparatus. Right? The particles are entering and then we are measuring. So, by physical process, okay, through electromagnetic process or optical process or chemical process, we could change the state of any quantum particle. It could be any arbitrary physical process, either manually induced, designed by human beings, or it could be some natural process. Whatever it is, the postulate says that any such process that is happening, either natural or artificial, okay, that can be represented as a unitary matrix. So unitary matrix means a matrix is called unitary if, so U is a unitary matrix if U dagger is equal to U dagger U is equal to identity. What is dagger? It's conjugate transpose. Okay. So that means you know the notion that if A is a matrix, AT means A transpose. Just row and column you interchange, right? You rotate. So that becomes a transpose. Now dagger, this notation means because U can have complex entries. It's a complex matrix. So you transpose and take complex conjugate. As in, complex conjugate means if the complex number is x plus iy, to take x minus iy. As simple as that. So a matrix will be called unitary matrix if it has the property that after you multiply the matrix with itself, after doing conjugate transpose, then it gives you identity. No matter U conjugate transpose or U conjugate transpose multiplied by U. Such a matrix represents any physical process that can happen to a quantum particle. So you imagine, suppose this is a single quantum particle, so it is a two-dimensional vector. So it has two components, suppose Z1 and Z2, two complex numbers. I can represent its state as a complex vector like this. Then this matrix would be a 2 cross 2 matrix. Right? So 2 cross 2 matrix. So suppose this is my vector, say V. So U times V, that will be my new vector V dash, that will be the output, that will be again a two-dimensional vector. So 2 cross 2 complex matrix, 2 cross 2 two-dimensional complex vector, another two-dimensional complex. So surprisingly, nature does not go out of this. So again, that has come from experimental observation. People have observed that any kind of change in a quantum system can be modeled mathematically as simple multiplication by unitary matrices. So when we talk about information processing and computation, we can forget the underlying physical process. So physicists can do research on implementing the physical process. Okay, and we can talk about only linear algebra. So it's just a linear operation, any state. So as computer scientists, if we want a specific linear transformation, we can tell the physicist, okay, I want this kind of change. So I want this matrix to be designed, and it's up to the physicist to design the underlying physical, chemical, etc. process that will do such kind of change. And vice versa, physicists have observed some kind of physical process and they have said, okay, these are the matrices that represent this process, and now we work with those matrices. And this is how things go on hand in hand. Okay. Clear? Next. Postulate 3. So to every observable of a physical system is associated a Hermitian operator. So again, Hermitian operator is nothing but a matrix, and it is called Hermitian because if it is self-adjoint. So that means if you take its conjugate transpose, it is the same matrix. Okay. So a matrix is called Hermitian. Any Hermitian matrix will have this property, H equal to H conjugate transpose. What it says that physically, whatever observable you can talk about. What is an observable? Anything. You can observe velocity. Okay, so velocity is an observable. You can observe kinetic energy. Kinetic energy is an observable. You can observe magnetic moment. Okay, magnetic moment is an observable. Whatever physically you can observe and measure, that quantity or that object that you are measuring can be modeled mathematically in the quantum world by a Hermitian matrix. So how you are changing state becomes a matrix. What you are measuring, that becomes a matrix. Okay. And what will be the result after you do the observation? This is how the observable is modeled. Fine. Now it turns out that if we have Hermitian operator in general in terms of linear algebra, if we have Hermitian operator on a vector space, then so any matrix will have eigenvalues and eigenvectors. All of you know that. So if we take the eigenvectors of the Hermitian operator, they form an orthonormal basis of the same state space. So that means the state can be represented as a linear combination of these eigenstates. Any state in this space can be represented as a linear combination of the eigenstates. Okay. And another thing is the Hermitian operator's eigenvalues are real. So these two can be proved by mathematical theory. Okay. But what it tells you further about the measurement. So that is the fourth postulate. So that means when you measure an observable, whether the observable is velocity or position or energy, when you measure, so mathematically the outcome of the measurement is one eigenvalue of the matrix representing this observable, and after the measurement the state collapses to the corresponding eigenstate. The eigenvalue that you observe, it collapses to the corresponding eigenstate. So every eigenvalue is associated to an eigenvector. Right? So here actually now I can explain you how this postulate model the experiments that we have been talking about. So when a measuring spin, say Z up and Z down, for example, so there this up and down are the eigenstates. Okay. And say the amount of deflection that we are measuring on the screen, that is proportional to the eigenvalues. So if we represent the magnetic spin, okay, so it will be plus half or minus half. So those are exactly the eigenvalues that are observed. And whatever be the state, so the state could be either initially in the up state or in the down state, or a combination of up and down state, a linear combination. So it need not be aligned with the basis, it can be at an angle with each of the basis vectors. But still, after you measure, you will observe exactly one of the eigenstates. Okay, so you cannot observe any arbitrary state. So the eigenstates form a basis, right? I can have many bases. So I have an arbitrary vector. So this is a state vector, a quantum state, which I am observing. The postulate tells us, and what is the postulate? Postulate is nothing but formalization of what you observe in nature. Why such kind of things happen, again we do not know. What is observed? Whenever we measure any quantum state, the measurement outcome, irrespective of what is the position of the state, correspond to one of the eigenvalues, and after the measurement, this state collapses to either this eigenvector or this eigenvector or this eigenvector corresponding to that particular eigenvalue that was observed. And there lies the uncertainty. So if there are 10 eigenvalues and 10 eigenvectors, all 10 are equally probable. So with probability 1 by 10 you will observe this eigenstate, with probability 1 by 10 you will observe this eigenstate, so on and so forth. Okay. So there, for example, there are two values. So with probability half you are observing z up, with probability half you are observing z down. Okay. Similarly for the x, you are observing x up and x down, like that. So anyway, so this I have already told you. This is just a summary. So this state, any quantum state is represented by this notation. It is nothing but a vector. So when you see such a notation, so scientist Paul Dirac, Nobel laureate, he introduced this notation. It's called Dirac's notation of a quantum state. It is nothing but a column vector, two-dimensional column vector. So alpha beta, where alpha beta are complex numbers. So alpha is x plus iy, beta is some gamma plus I delta. And it is normalized. That means modulus of alpha square plus modulus of beta square equal to 1. That's the normalized vector, which is the English vector. So any state of any single particle can be represented like this, be it an electron spin, be it a photon polarization, be it anything. Okay. And when we measure, suppose we have a basis, suppose this is the eigenbasis. So M1 and M2 are one particular basis. And we are doing a measurement, so the probability of the outcome of observing Mi is just a dot product between psi and Mi. Okay. And when you talk about transformation, every available physical transformation can be thought of 2 cross 2 unitary matrix U on this state. So U will be applied on this. And in particular, this 1, 0 and 0, 1 is a particular basis because any complex. Okay, so let's. So this is basic linear algebra, which I hope all of you have done. So any complex vector, say Z1 and Z2, it's a complex vector. So what I can write? I can write this Z1 times 1, 0 plus Z2, 0, 1, right? So these two are special vectors, right? Sometimes in mathematics you write them E1 and E2, right? In physics you write I, J, K in that terms. So I can have different bases, but this is a particular basis of the vector space because any two-dimensional vector I can write as a linear combination of this vector. So this is also a vector in that space because 1 and 0 are also complex numbers. 0, 1 is also a vector. So these two, 1, 0 and 0, 1, these two are two special vectors, okay, which happens to be a basis of that space. So these vectors are given a special notation. So this is given the notation 0, and this is given the notation 1. So when we talk about qubit, few slides later, a quantum bit. So a qubit 0 is nothing but this, which is nothing but this vector, which is nothing but some state of some physical particle. So either horizontal polarization of photon or say upspin of electron. Just like when you represent 0 in classical computing, it's either high voltage or high current or high charge or the other way around. Okay, 0 and 1 are the opposite. Sometimes you have low logic or high logic. One of the two. So similarly here, so when we want to build quantum computer, we have to work with quantum particles. So there, the quantum 0 or the qubit 0, nothing but corresponds to this notation, which is nothing but this vector, which is nothing but physically, whatever system we are using, if it is a photon, it's either one of the polarization state, or if it is electron, is one of the spin state, or it's some other state of some other particle, if we are using that. Clear? But what is the difference? The difference is, in classical computing, we can have the bit value of either 0 or 1. Not both together. But here, because any linear combination of these two vectors is also a valid vector in the same space, as long as it is normalized. So, just like this 0 vector and 1 vector are my 2 qubit, similarly, this Z1, Z2 vector is also a qubit as long as I have mod Z1 square plus mod Z2 square equal to 1 unique vector. So it could be say 1 plus I by root 2, some strange complex number. It could be some other strange complex number, right? But that is also a valid quantum state. And that can be represented as a linear combination of the 0 qubit and 1 qubit because these two form a special basis. And this special basis is also called the computational basis because the computation or quantum computation is done using this kind of basis. Okay. So then from one to many particle, I don't want to go into detail. So one to many particle, it becomes a tensor product. Tensor product is nothing. You take all possible combinations. So you have one particle in state, say alpha 1, 0, beta 1, 1. Right? So this can be written as Z1, 0 plus say Z2, 1. So Z1, Z2 are like alpha 1, alpha 2 complex number. Second particle could be alpha 2, 0, beta 2, 1. Right? So when we talk about the joint state of the two particles, then it becomes a product like this. So this 0, 0 is nothing but a shorthand. So this is a 2 qubit state. If you talk about quantum register, this is a 2 qubit quantum register which can contain either 0, 0 or 0, 1 or 1, 0 or 1, 1 or any linear combination of them. Linear combination by complex scalar multiple. Okay. Those are precisely alpha 1, alpha 2, beta 1, beta 2 number. And mathematically this 0, 0 is nothing but this 1, 0 vector cross product 1, 0 vector, not cross product, tensor product. So tensor product is nothing but it's this 1 followed by 1, 0, then 0 followed by 1, 0 like this. So this becomes, this is scalar multiplication, so 1, 0, then 0 multiplied by 0, 0. So first I multiply 1 into 1, 1 into 0, then I will multiply 0 into 1, 0 into 0. So I will keep this fixed, I will use each one of these coordinates. So that's the definition of this multiplication. So it becomes a 4-dimensional vector for two particles. Because there are 4 bases, you see, 4 computational bases. So for two particles, it is a 4-dimensional vector space. Every vector has 4 coordinates. So for n particle in general, things becomes now messy. Because in classically, n particle, n state, you have n bits, either 0 or 1, right? And at any particular time instant, you could have exactly one of the 2 to the power n possible values, right? Now here, you can have any one of the 2 to the power n possible values if you have an n qubit quantum register, or it could be a linear combination of all of the 2 to the power n possible values. And because those are exactly the eigenstate, when you measure the quantum register, that means when you probe the register, try to read out the value. Measurement means say read out. When you do the readout operation in computer, you will not observe the arbitrary state. You will observe exactly one of the eigenstates. So then you cannot distinguish with classical register. You will observe exactly one of the fixed the basis states with some probability. Okay. Then there are some strange facts in quantum domain. I will just try to highlight. So we have talked about bits and physically how to represent bits. So maybe 10-12 minutes. Finish. So you can now relax a little bit. So I promise there will be no more, abstract algebra. And just to quote Albert Einstein, he actually has a famous quote about this, the algebra or the calculus that is involved in the quantum domain. He called it is a black magic calculus. Because the axioms are very strange, and your assumptions are strange, the outcomes are strange, and of course it has to be because it tries to match with the physical world that we observe that is strange, which we justify through the experience. So no more black magic calculus. So we try to focus on some notions. Yeah. So classically, when there is a communication, okay, so you are sending one bit from A to B through wire or through wireless or whatever be the reason. So we can always copy the bit without disturbing it. Okay. So in, say for example, in cryptographic scenario, if you are sending encrypted message, so any attacker can copy your encrypted text without even informing you. You cannot even read it. Okay? Because there will be no alteration. Surprisingly, in quantum domain, you cannot copy. Whenever you try to copy, it will actually destroy the state. So it will again collapse into one of the eigenstates. So it was a linear combination, now it will collapse. And just the proof, so the proof of this theorem, it is called a no-cloning theorem, was in 1982. It is a roughly 3-page paper, was published in Nature. Just the proof, and it uses nothing but basic linear algebra. So that gives security in communication. Very well appreciated. Another strange fact in the quantum domain is quantum entanglement. So that means two particles. So entanglement means some kind of correlation. So two particles will be entangled or correlated in such a way physically that when you measure one particle, you will get the information about the other particle for free. Even if these particles are separated in space, not even on Earth, but even two different galaxies. So I can prepare an entangled pair of electrons in my laboratory and send one electron to outer space. Still the entanglement will remain. And by doing some measurement on one particle, I can always predict the measurement on the other particle. And how to create entanglement? Very simple. There are very simple unitary operators, again some matrices, which you multiply your state and then you get an entangled state. As simple as that. And mathematically, entanglement is represented by something. So we are talking about two particles which are physically entangled. So the state of the first particle is nothing but something like this. Alpha 1 is a complex number, beta 1 is a complex number, 0, 1 are the basis vector. The state of the second particle is like this. But when you write out the product, it is nothing but alpha 1, alpha 2, 0, 0, then some combination 0, 1, 1, 0, 1, 1. All the terms are present, right? Now suppose the state is something like this. Say 0, just a short example. So say 0, 0 plus say 0, 1 by root 2. I am writing root 2 because I have to normalize it. Modulus square will be 1. So this we can write as product of two different states. Why? Because I can take 0 common and then take tensor 0 plus 1 by root. So this is a normalized state, this is a valid normalized state, and this is a product, because by the product rule, you can write 0 times 0, 0 times 1, it goes here. Okay. So this state, this two particle state can be written as a product of two single particle state. In such case, we say it is not entangled. If such a factoring of state cannot be done, that means mathematically I cannot talk about the state of particle 1. Particle 1, particle 2 joint state I cannot write as a product of two states. That means there is physically no notion of a state of this particle and the state of this particle. I always have to talk about the joint state. One example is this state, 0, 0 plus 1, 1 by root 2. You try to factor out, you try to write down as a product of two vectors with any coefficients, any combination of 0, 1, any combination of 0, 1, you will fail. It cannot be factored. So such a state is an example of an entangled state. Okay, and there I cannot talk about what is the state of the first particle. I cannot. What is the state of the second particle? I cannot. The joint state is 0, 0 plus 1, 1 by root 2. And when we measure the measurement laws in the postulates that we observe, that tells us that I will observe 0, 0 with probability half, because this amplitudes, this coefficient square is the probability. Okay, and that's why we normalize vector, because the sum of the probability have to be 1. So because it's a normalized vector, sum of the squares should be 1, and that represents the probability. So and this, the probability of observing this outcome will be half, 50-50, right? Now suppose I create a entanglement pair in this state, take one particle to the other world, keep one particle here, I measure this particular particle. And after I measure this particular particle, it will be one of the eigenstates. Suppose the value is 0. So as soon as I observe that okay, the state of my current particle is 0, I know for sure that the state of the other particle is 0. Because 0 means it has to occur with this 0. Because 0, 1, 1, 0 are missing from the joint state. So this is 0 means the other has to be 0. Similarly, this is 1, the other has to be 1. So I did not measure the other particle, but still I can predict the state full. And such a strange phenomenon of entanglement is practically used in superdense coding. So superdense coding means classically, in order to send 2 bits of information, you need to use 2 bits. You cannot use 1 bit to send 2 bits of information. Okay. So that will break Shannon's entropy laws. But in quantum domain, using entanglement, you can send 2 classical bits of information using only 1 bit. Okay. So that is one interesting thing. One cube. Quantum teleportation. So teleportation again, all of you have heard the term from the movie Star Trek, where a person disappears from, one place and reappears at another place. Okay. You have seen in movie Matrix also that when the phone call comes, the person receives the phone and disappears from one place and reappears in the other place. So that's teleportation. That really happens in quantum world. So in 1 minute I will explain the idea very briefly. So suppose we have particle A and B here, and we have a particle C here. So we have to have an entanglement between A and C initially. That is very easy to create. We have unitary operators for that. Now, we can do some measurement, joint measurement on A and B together. So that will force the particle C to acquire the state of particle B. So that means B can have any arbitrary state. Suppose it is alpha 0 plus beta 1, where alpha, beta are unknown complex numbers. We do not know, it's an arbitrary state. I want to send this state here. This particle initially will be some other state, because A and C will be entangled, and B has no correlation with A, B has no correlation with C. What I will do? I will do a joint measurement here. You can just calculate the basic math using the postulate that I have described. Simple linear algebra will tell you that will facilitate you to recreate this state here. So the state of B transmits to state of C. Right? That is one part. So physically, how can we achieve the real teleportation that is portrayed in science fiction movies? So you can think of your physical body to be constituting of many particles. Right? At the end, we are electron, protons, and neutrons. So we are made up of some molecules and then some atoms, and finally some electron, proton, and neutron. So if we can teleport each and every electron, proton, neutron, or could be any other fundamental particle that is present in the body using such kind of technology, then teleportation is of course possible. And that is a huge task, because even copying one particle is very cumbersome. The state of one particle. Transmitting the state of one particle. So what to speak of transmitting the state of many particles of a body. But there is another catch. The another catch is we are not sending this particle physically. You see? The state of the particle reappears as state of some other particle. So that means what? Physically, even if teleportation is possible, means nothing but some technical way to manage transmission of state of multiple particles. If we can achieve that, teleportation is physically possible. But that means myself will not physically be transmitted. So some other state of particles in the other end So my particles will collapse. So my physical body will collapse here. Some other particles in some other area will reassemble together to form my structure. That will be the teleportation. But then, will it transmit your mind also? Will it transmit your brain also? Your memory also? Or will it transmit your identity also? Consciousness also? That question is very tricky. Nobody knows the answer. So one school of scientists think that our self-identity or consciousness or whatever psychic identity we have, that is a manifestation of our physical body. So mind is a product of matter. So they believe that okay, it can be recreated. But there are many other scientists as well who believe that our real identity is not this physical body. There is a metaphysical entity inside us that creates our consciousness, self-awareness, identity. Some people call them soul, some people call them consciousness. So because that is not a physical entity, so through teleportation that cannot be transmitted. So ultimately you will create some statue. Like this. So anyways, that's the debate. Next is quantum cryptography, which I briefly explained that because of no cloning it is possible. Next, quantum algorithm. So I'll just briefly give an overview without going into detail of each possible algorithm. Just I will name the algorithm and what it does. So this quantum computing started with Richard Feynman, 1982. In 1985, the first quantum algorithm was invented. And quantum gate, as I told, gate is what? Gate is nothing but a device. You give some input bits, you get some output bit. In quantum gate, you will give some input qubit, you will get some output qubit. And as I explained, any state change is nothing but a multiplication by unitary matrix. So any quantum gate, these are the name, these are the notation, is nothing but multiplication by some unitary matrices. So you want to physically realize a quantum gate, you have to do some physical process such that in the end it represents this matrix multiplication. As simple as that. Okay. And the quantum computer will be nothing but a combination of these gates. Okay. So quantum algorithm is actually more advantageous than classical algorithm for some problem. So one example is the Dwight-Dosha algorithm decides whether a Boolean function is constant or balanced. If you have a Boolean function of n variable, it can be represented by a truth table of 2 to the power n rows. Right? Everybody knows that. 2 variable Boolean function 4 rows, n variable Boolean function 2 to the power n rows. Now, if I promise you that my function is either constant, that means the output column of the truth table is either all 1 or all 0. That means constant. Or it is balanced. That means there is equal number of 0 and equal number of 1. Right? I have promised you either constant or balanced. And I am asking you that you try to design an algorithm to find out whether it is constant or balanced. Now, by classical means, it is not possible to solve in one query. Why? Because you need to at least scan through half of the truth table. Because if it is back, so suppose you have observed 0, 0, 0, 0, 0 up to half of the truth table, right? You still do not know whether it is balanced or constant because you have not observed the other half. If the other half are also 0, then it is constant. If the other half are all 1, then it is balanced. So you need to check at least half plus 1. So if you have 2 to the power n entries in the truth table, you have to check 2 to the power n divided by 2 plus 1. So that means 2 to the power n minus 2 plus 1. That many queries you have to make to the function. Right? Then you can know. Because if there are half plus 1 when is 0, you know it cannot be balanced. Therefore it must be constant because it promised to be one of the two. So the complexity in any classical algorithm must be of the order of 2 to the power n minus 1 plus 1. That's the classical complexity. Surprisingly, in quantum algorithm, that means using some unitary operation, some measurement, using the same postulate that we have said, basic linear algebra, he showed that it can be done using one query. So you will call the function 1, so big O of 1 from big O of 2 to the power n minus 1 plus 1. So it's an exponential improvement. Similarly, if we talk about database search, if you have an ordered database, then you can search in log n operation, binary search. But if it is not ordered, then you have to do sequential search. So the worst case search complexity in classical algorithm is order n, big O of n, because you have to go through all the entries. is not solved. Grover showed in 1996 that we can design a quantum algorithm where any unsorted database can be such an order square root of n time, which is a huge improvement. Okay. So unsorted database means ultimately we have some index. Those index can be represented binary in bits. Those bits can be represented in qubit. Those qubit can be manipulated using unitary operators, and then finally some measurement. You will get some qubit that can be represented as a bit, that can be represented as an index. You will get the database whether it is present or not. Next. Similarly, factoring problem. So classically, factoring is very hard. So no polynomial time algorithm is known, but Peter showed in 1994 that in log n cube time you can actually solve factoring. And that actually is a big problem for classical cryptography, because there are many classical crypto systems, for example RSA crypto system, that uses the hardness of factoring as its security. So you go to any, many of you use Flipkart, right, or Amazon.in. So it turns out that any e-commerce based website uses some variant of RSA for security, and that involves it's difficult to factor a number which is product of two primes. But if you have a quantum computer, then just log n cube, that means even smaller than n cube or an n cube, very trivial running time, you can break factoring. That means you can break any such e-commerce based system and many other crypto systems as well. So that's a big problem if quantum computer comes. But we have hope, because now people are doing research in post-quantum cryptography. That means they are assuming quantum computer is here, all the classical crypto system based on RSA and similar problems suppose are broken by quantum computer. But still, can I have some classical algorithms which are immune to quantum attacker? And it turns out indeed there exists some classical crypto system based on coding theory, based on integer lattice. They are immune to quantum attack, and those are called post-quantum crypto systems. So even the quantum era appears, we have results on post-quantum era. Okay. And this is just a brief overview of the complexity class. So this is polynomial, bounded probabilistic polynomial, NP, all the computer science guys know, bounded quantum polynomial. So that's why you have more advantage than the classical computing. But the problem is the connection between NP and BQP is not known. So just because factoring and other problems can be solved efficiently, that does not tell that all NP-compute problems can be solved efficiently in quantum domain, because the relationship of these two classes is not known. So that's an open area. This is just a list of physical implementation of quantum computer. So as I said, you can use many things, just like in classical computation you use charge or current or voltage. Here you can use many physical properties of many items. This is the outline of current global scenario. So the latest one is in December 2015. Many of you have read the news report that NASA has announced, and they have invited all the media to actually check their first fully operational quantum computer, and they claim it is over 1000 qubit. The previous one was by 512 qubit. That was an excess between NASA, Google, and USRA. Okay. So, and NASA actually claims that this can be used to do better prediction, better weather prediction. And there are some websites which I have given. You can go and buy their true random number generator. Classically we can always generate pseudo random number generator. We cannot generate true random number, but in quantum domain it is possible. So now they sell a USB stick. So inside the USB stick there is quantum circuit. You can put your USB stick in your normal ordinary laptop or computer. You can run the program. It will induce the physical quantum process inside the USB, and it will feed you with truly random bits which you can use for your program. So that is the reality now. So this is my last slide. So I will just wrap up with some interesting connotations. So one connotation I already mentioned regarding teleportation, right? So from physics to metaphysics. So I talked about consciousness issues in the teleportation scenario. So many physicists believe that consciousness of the observer interacts with the system to create the result. So as I explained in the double slit experiment, right? So as if the particle is choosing which slit to go through on its own, right? Or when to go through two slits, when to go through one. How is it possible? It cannot be explained. So some scientists believe that, and among them there are many Nobel laureates and many famous scientists in physics, they believe that the observer or the real human being who is actually measuring the quantum system, the consciousness of the observer interacts with the particle and creates this randomness. Okay? And there are many computational theory of mind or consciousness nowadays. One of them, very famous, by Hameroff, who is an anesthesiologist, and by Penrose, who is the PhD supervisor of Stephen Hawking, famous mathematician and physicist. So they have a model called quantum cellular automata in microtubules. Microtubules are some string-like structure inside our cell cytoplasm. So they are modeled it. Some quantum cellular automata is running inside our cell cytoplasm, which is creating this mind and consciousness kind of thing, though it is much debated. And last but not the least, in 2012, the premier journal Physics Essays, there was a paper which reports 6 experiments, not one, 6 experiments that demonstrate that meditator, they while meditating can influence the measurement of a quantum state, quantum device. So there is some quantum system which is physically away from the meditator, and during the measurement the meditators are asked to focus on either on this state or that state, and it was observed that through their meditation powers they could actually bias the result. So it is available, you can, if you are interested, you can read. So that's why I gave the name to this slide, Physics to Metaphysics. And we do not know where it will lead us to. So it's an interesting area, lot of open issues still there, both from physics research, how to physically represent a qubit and manipulate a qubit, and both from computer science research, information theory research, and metaphysics research. So I'll end my talk and access any questions there.
Okay, so first let us thank the talk. And any questions, quick questions? If you have any?
Yes.
So you talked about the entanglement theory, right?
Entanglement, yeah.
Entanglement. So in entanglement, how the information is propagated from one particle to another particle, the state information. When you were just saying that the state is changed, but
Yes.
how?
That's a very good question. So see what is happening. Suppose you have this state. Say, so I am giving another example, and it is the same. Suppose it's a shy state, 2 particle state, particle 1 and 2. 0 1 plus 1 0 by 2. I could have 0 0 plus 1 1. The one that I gave example. But it's the same. If you have 0 here, you will have 1 in the other particle, and vice versa. It cannot be factored. So the thing is that when you do measurement on the particle, say at place A, maybe I should write them A and B. So this is say 0A, 1B, say 1A, 0B. Then it becomes easy for you to observe. So when I observe at system A that my state is 0, I know that in the other system my state is B. Fine. Now the point is, people thought that it is a superluminal communication. That means you can communicate faster than light, because instantaneously the information is being transmitted. But the fact is, the information is not instantaneously transmitted. Why? Because consider there someone is trying to measure the particle, right? The state of the particle. Now that person, how that person will know whether you have received this 0 or 1? So if that person somehow happens to know that without measuring his or her system, that okay, you have observed 0, then he or she will conclude that okay, after I measure, my state will be 1, even without the measurement. Similarly, if that person knows that your system is in state 1, then after post measurement state of his or her particle will be 0. Right? But before I communicate from here to that person that I have received 0 or 1, that person cannot know. So actually there is no information propagation. Information is what? Knowledge about the system. So knowledge about the system, I know the knowledge about the system because I have created the entanglement at my place and sent it. Or at least I have been told, even if it is prepared by someone, I know that the state is 0, 1 plus 1, 0. Right? So that information is already with me. So now when I observe 0 or 1, I am extracting some classical information, so I am getting the other information. But the other end, that person needs to know. So that means I have to ring some telephone and call that, hey, I have received 0. Then that person will know, okay, then my state will be 1, even if I don't measure it now, even if I measure later. So that phone call and transmission of the information regarding the result of the local experiment at system A is by using classical links. Right? So that will not be faster than light by special theory of relativity. So entanglement actually does not break special theory of relativity.
So I mean that whenever you are creating the entanglement, so some information is already embedded in the particle, right?
Right, but that information is not accessible to the measurer, to the observer.
The observer there.
Right.
Now I am saying that can the particle state change after creating the entanglement, and that change will be reflected there. Will this happen? That will not happen, right?
I didn't understand. No, that could happen if I do some unitary operation.
But that is a logical operation, right? It will not be changed physically. I mean, even if I represent the physical state in some quantum state.
But that is happening, right? Otherwise, teleportation, how it is happening? Teleportation.
That is the question I'm asking. If that is happening, then how that is happening? Is there an explanation?
Oh, that nobody knows.
Okay.
Physically, why it happens?
Physical.
If people knew, then the subject is already closed.
Okay.
That's what maybe you came late. In the very beginning, I mentioned that in the real world, we do not know why something happens. At least for everything. Some things we definitely know. I should correct myself. For everything, for every observation in this world, that is scientific observation and that can be transformed into scientific laws. For every such observation, we do not have an answer why it happens. We know when it happens, how it happens, and we model it to process it. And phenomena in the quantum world are such kind of events. There are many theories, but those are all theories that how this happens. Okay? There is something called hidden variable theory. That okay, there is some hidden variable that is acting on the system, and then you are manipulating those variables. There are many other theories, but none of them are conclusive yet. So it's still open.
Thanks.
So, if you have any more questions, you can always contact Gautam. So Gautam comes right up and note down his email ID and having an interesting content, so you can just visit. So with this, let us thank Gautam again on behalf of IEEE Computer chapter for the section. Thank you very much. So we have a small snacks package. So